Okay, so having discussed the basic conceptual framework of particle filtering this morning, my thought was this afternoon to seek to take a look at a model which uses particle filtering. This shouldn't take more than about half an hour, I think, but it will give you an illustration of how it works. And perhaps Kurt could apply his combination skills to this thing again. I didn't catch it when you were doing it before.
I'm not sure I remember now.
So within this discussion, I wanted to thanks, Kurt. I wanted to take a look at one particular model. It's not particularly privileged, but it's a model that's associated with a paper that we published that will illustrate the basic functioning of a particle filter. And to spare my throat, I'm going to put on this microphone. It will amplify my voice because my computer has to pick this up, and the computer is recording it, and so I didn't want to have to yell if I'm across the room. Okay, so I have a model here which I've begun to share with anyone, which formed the basis for a paper we published. We have accepted, and it's going to be published later this year, which is examining the effectiveness and feasibility of particle filtering in the context of epidemiological modeling. It's a particularly simple scenario where we imagine a situation where we have some underlying epidemiological context that's fairly textured. In this case, we have a situation where we have agents within networks. Each agent is described by has a state chart given by these criteria. And they communicate, as is typical within agent-based modeling. They communicate with each other according to to messages. Individuals can in some cases be starting in the effective state, but otherwise people start in a susceptible state. And these individuals are wired up into networks of various sorts. And we tested this in a variety of types of networks. I think it was scale-free, small world, Poisson random, and distance-based, I believe. And we examined the ability of the particle filter with an aggregate model to accurately anticipate and predict what was going to be playing out and to match what was coming out. And we did that with and without particle filtering. In other words, particle filtering on a regular basis or with no particle filtering at all. We further examined the impact of a situation where we in the particle filter, we allowed a parameter to vary, and we saw how much effectiveness it could achieve. So we examined, in short, particle filtering with a model that was significantly off from the underlying situation, and a model that was where C was allowed to vary and could eventually it could learn values of C essentially that were more appropriate for the model under consideration. So models with systematic errors, how well the particle filtering perform, and models just with a lot of uncertainty, but which could accommodate the underlying model behavior. So that was kind of the setup. We ran a particle filtering within an SEIR model, and we used the particle filter to correct it, and we compared it against the situation where it was uncorrected. I'd like to focus the issue on looking at the nature of this aggregate model for which the particle filter was being applied. You'll notice here that within Anylogic, the stalks and flows of the model are shown here. You'll see there's a susceptible, exposed, infected, and recovered. And this is a familiar SEIR model for those who have taken my modeling class before. As familiar, we have an assumption of random mixing. This is very vanilla stuff. We have some number of contacts per week, some prevalence of infection, the population as a whole, and some force of infection deriving from that. And that force of infection, that chance per unit time an individual will be infected, is multiplied by the number of susceptibles to get the number of new infections per unit time. With one caveat, that actually this number of new infections is a stochastic process by which there's actually and I'm going to have to go select it here. Okay, yes, it's actually a Poisson process. So there's a force of infection and some number of susceptibles that are subject to that force of infection, and then we're actually applying this draw from this Poisson distribution for each time step to see how many people actually transition here. So we're integrating this in very small time steps, and we're seeing how many transition, and that's a discrete process. This lends some stochastics into the situation. You'll notice there's also a process by which we can involve a parameter C that is of fundamental importance here, and I'll come back to that in a minute. So there's two stochastics, one associated with this and one potentially associated with C, where C evolves over time. The most important thing, however, to emphasize about this model is the fact that each of these stalks is subscripted by particles. And what I mean by that is that for each particle, there's a complete copy of the model state. There's a complete copy of the current state of the model. So the number of susceptibles, number of exposed, numbers of infections, and these flows as well are all subscripted according to the particle. So each particle, particle 1, particle 2, particle 3, has a complete copy, a complete layer, as it were, of this model on its own. Similarly, this contacts per week up here, force of infection, etc., these auxiliary variables are also subscripted according to that. And notably, each particle has its own value of C. In this case, I'm representing it as log C, but you'll notice it too is subscripted by particle. This subscripting hews to Anylogic's typical use of subscripting in models. In this case, there's 10,000 particles. You'll notice the particles are 0 through 199, or through 9999. So there's 10,000 particles within this model that are running simultaneously, each with their own copy of this model here, of these variables, and their own copy associated with C there. So here we have a situation where we have the basic dynamics of the model described with this set of stalks and flows. What's important to note is that this is very straightforward to do with stalks and flows here. Conceptually, it could be readily applied with agent-based modeling. We could have conceptually a full copy of an agent-based model for each particle, but that's
that's a heavier weight operation. And then keeping a full copy of an agent-based model requires a lot more memory, and there's a lot more mechanisms involved. For example, keeping a full copy of the network. This is one of the reasons why we're talking with Ivan and Chris Duchin about building particle filtering into the agent-based modeling language for objects that we're evolving, rather than having to impose it. But for system dynamics models within Anylogic, such as shown here, it's a very straightforward thing to impose. You simply subscript it accordingly, systematically subscript the different variables, and that allows it to run separately for each particle. So that's element one.
Now, let's dig a little bit deeper here. So what happens here in this model is periodically there's an observation which is received. You'll notice this thing that's called received empirical observation. That's an event which fires periodically. Now, in this case, for simplicity, you set it so that it goes off every week in the model. The first occurrence time being at week 1 rather than week 0. So the first piece of data is received at week 1. And it goes off at precisely that time. There's no particular, that's not a privileged schedule. We could, in general, assume an arbitrary schedule with irregular spacing between these, and the particle filter works just fine. There's nothing that assumes that the schedule must be regular. But in this case, it is. And my point in showing this is not only to emphasize the generality there, but to note that when a measurement is received, a number of things have to take place. So, number one, we record the number of empirical observations that have been received. We accumulate information on the discrepancy. This is for reporting purposes in our paper. We want to be able to quantify how much better a model that was particle filtered was than a baseline model without particle filtering when comparing with compared with each other. And the way in which we did this is just before observations were recorded, we looked at the discrepancy between the model findings and the ground truth data from the agent-based model. And we accumulated some discrepancy for that. So it's a huge amount of discrepancy. And then there's some stuff to update some histograms to kind of give us a sense of what's going on. Now, if a particle filter is being performed, we process a new empirical observation for particle filter. And in any case, we update the histograms for the posterior, and we report the mean values for the estimates, just as much for debugging as anything else. So what I wanted to focus on here, because our attention is on this case where particle filtering is performed, I wanted to look at this process new empirical observation for particle filter. As normal, my naming doesn't give a lot of guesswork as to what this does. So here's process new empirical observation for particle filter, and if we look at this, this method, it updates the weights based on the observation, and then if the effective sample size is less than some number, in other words, if we have too big a variety of weights, too big a range of weights involved, then we do this resampling step. That's this step over here on the board, where we take all the weighted particles and we draw from them, and some survive and some perish. We draw from them according to their weights and normalize all or we set all the weights to be 1/n in weight. That's the resampling step he described here. That's the survival of the fittest. So we don't do that every time, partly for computational efficiency. We do it when the weights are too varied, the weights that we have in effect.
The main thing I wanted to draw attention to was this update weights based on observation.
Let's drill down to that. And that indeed is right here below this. So updating the weights based on the observation. Some code to clean up here. But basically we get the empirical data for the, for the current time. And then we actually, and we round that to an inch, so that we can compare it to the actual number of individuals within the model who are in that state within the ground truth model. And now, within this, so we can perform draw from binomial distribution, as I recall. And so then what we do is we get to each particle, and for each particle, we get the number that have completed the latent period, which is a count, an integer count, within the past, well actually this is a rate, this is a rate here, and then we compute the likelihood function based on the empirically observed infectious numbers, that's this one up here, and based on the actual incidence from the model. So this simulation model, so in other words, this is from the stock and flow model, this D model incidence. So here with the empirically observed one, in this particular model that happens to be from an agent-based model, but in general could be empirical data. And we basically ask, what's the likelihood of observing that, given that we actually have this amount of this incidence in the posited in the stock and flow model. So if we posit this incidence in the stock and flow model as given by the flow, here, the number completing the latent period, what's the likelihood we would actually have observed this empirical data? And based on that, we take the weight prior to the update, and we multiply that by the likelihood to get a posterior weight, and then we basically assign that posterior weight to that particle. And we go through some stuff to normalize them as well. We sort of total up the total, and then we normalize them so that they all total up to 1. So this is sort of the heart of the particle filter right here. It's going through each particle, and for each particle, it's assessing what the likelihood is for that particular particle of having the of observing the empirical data, which are shared across all particles, for what's posited by that particular particle. That particular particle posits a certain number of people completing the latent period, and we assess what's the likelihood that we would have observed the empirical data in light of that that value that's used in the model. So in other words, this completing latent period is this flow right here. So that's the one. Each particle is a separate value of the flow. That's why it's subscripted by particle. So for each particle, we are going through and asking for that particular flow, how plausible is it, in other words, that we would have observed the empirical data in light of the value of the flow that's posited by the model. If the empirical data seems very plausible, the likelihood will be high, and we'll be multiplying the posterior weight will be a large value, a large coefficient times the prior weight. On the other hand, if this completing latent period is completely implausible in light of if this empirical, this data here for this flow for the particular particle makes the empirical data seem very unlikely, then this likelihood will be very small, and we'll multiply by the prior, and we'll get a very low posterior weight. So in short, the weights for particles that are fit, that exhibit good match with the empirical data, will tend to be higher than the weights for particles which posit a number of people completing the latent period that's deeply in discrepancy with the empirical data. This likelihood function that we're using here could be any number of different things. We happen to have chosen a fairly simple form, so likelihood of reports given infection count, and we can go find it here. Let's go see where it is. Likelihood of reports given infection count. Here it is. Okay, actually, sorry, no, that one was disabled. It's this one here. So let's go take a look at this. In this case, we've assumed a very simple one. So this takes in a number of reported cases. This is the empirical data, and then this actually says count infective. I think that's the infection incidence, but no, it is okay. I'm going to have to look at that. But in any case, so then we have a probability of a positive test report, and here we're drawing from a Pascal distribution, which is a negative binomial. So a negative binomial distribution, we're basically asking what's the probability of getting this total number of reported cases when we actually have a certain number of infective cases. In any case, this is the basic setup, and you'll notice that here, that's all within this update weights based on observation. If we have to resample, we have this resample and update weights in particles, and that is over here. Yeah. And so here we update the particle values with resampled indices, and we initialize uniform weights. So here we resample the indices. So this gets back a bunch of, we basically say, okay, the first one will take particle 3, the second one will take particle 1, the second one will take particle 1, the third one will take particle 3, and then we update the values accordingly. So in other words, we update the states, make copies of those appropriate particles, and then we initialize the weights. So that's attention particle filtering here within this model. The model, as you imagine, exhibits a fair bit of computational load to run. Here we have 10,000 particles. Just for the purposes of demonstration, I might change it to 1,000 here. And I don't remember the final state I left this in, but I believe it was in a state. So here what we see is this running, and here's the number completing the latent period. You'll notice this is changing over time as this model runs forward, and you'll notice it's subscripted by particle, right? And here we have sort of distributions associated with the number completing the latent period. Here's associated with ground truth, and then this is I'm going to have to check. This is pre-measurement distribution, and then right. So this is from the model. This is the distribution before the measurement, and then there's a ground truth over here. I can't see it here on the diagram, but there's a there's ground truth shown as well. And so fundamentally, you have a difference between pre-measurement and then post-measurement when it actually corrects to take into account the ground truth. These are various draws from different values. So this model is running. You can see it kind of selectively culling these various particles here as it's trying to kind of pull down the distribution. In this case, what we have is we have C also being perturbed, so there's adjustment going on over time to the value of the contacts per week. You can see these adjusting over time according to a random walk as well. So here we have the model running with 1,000 particles, and each particle has associated all these state variables, these auxiliary variables, as well as values for these contacts per week. And you can see this, these estimates being pulled here. So anyway, that's the basic setup of the model. What this requires is, as far as mechanism, is pretty much the same for different models. In other words, within different models, you're going to be putting in place very similar mechanisms. So to adapt it to another stock and flow model, you'd have to take that stock and flow model, subscript it by particle, and that includes both the stocks and flows and any components here. You may want to impose distributions on parameters or even random walks on parameter values if you think they may be evolving over time. And then you're going to have a pretty standardized set of mechanisms here to receive an empirical observation, process it, update the weights based on that, perform resampling when required for those weights. And you're going to need a likelihood function that's going to be specific to your particular model, that's going to report the likelihood of having observed the empirical data given the model state. In this case, the likelihood of total reports given the effective count. So anyway, that's the basic scheme there for a particle filtered model within Anylogic. Not too bad to build, actually. Yes, Kurt.
This seems to be a little bit at odds with hybrid modeling. Since it's already difficult to do with agent-based modeling, how would you apply this approach to something as complicated as a hybrid model?
I hope that for
future generations.
Not well, hopefully it'll be myself in another year or something, but I mean, it's interesting because this very model that we're looking at is a hybrid model, right? In the sense that we have the stock and flow model. I'm talking about the particle filter doesn't require hybrid modeling, but this particular application of it, where we're drawing data from an agent-based model to test the particle filter, and then we have the particle filter running as an SD model. That's a hybrid model, right?
Is the agent-based model running at the same time?
Oh yeah.
Oh, okay.
Oh yeah. Here, let me.
I thought it was data inputted from a previous.
No. I wanted to be able to run them at the same time so I could vary things and see how it impacted the results. So to make that clear, great question. So here's this model, obvious stock and flows running, but somewhere here I could actually dive down to it in another way. But somewhere in here, here we go. Yeah. There's that model, and here's the ABM population running. You can see these people on networks. This is a scale-free network, I think, in this case. And they're knit together.
But that's just simulating real data. I mean, that's just simulating the understanding of ground truth.
That's correct. This is purely generate ground truth data.
Right. So
to judge how well the SEIR model is inferring what's really going on in the ground truth.
Right, so an actual application wouldn't have that.
Correct.
So it would be a hybrid model.
This is It's not that particle filtering is inherently a hybrid process. It's just in this particular application, we're using a hybrid model with part of it being with stocks and flows, right, for the particle filtered model itself, and then the part generating ground truth being ground truth information.
Could part of the solution to using to agent-based model, like to subscripting agent-based models, be brought with aspects, the stuff that we were doing?
Funny you mention that. Yeah, I think I may have even ventured that idea a little bit in a group meeting with Chris Duchin. And I think your idea has a great intuition behind it. So for those not familiar with aspects, Priya's reintroduced them earlier, but aspects capture cross-cutting, where is this thing? Aspects capture cross-cutting functionality within programs, or in this case, models, right? Where's my, of course, I've got to go up. Boom. They capture cross-cutting functionality. In other words, some elements of structure that you see repeatedly across a program, or in this case, across a model. So an example of this that Prayasri talked about was logging, right? Like if you wanted to log and point out what a model was doing, you can go insert essentially print statements, trace cell end statements, all across the model systematically. But the point is that's a very systematic thing you're doing, say, for every state chart across an entire model, for the person state chart, for the deer state chart, for the state charts associated with seasonality for the whole environment. You're going in and you're putting in these trace cell ends. That's a cross-cutting element of functionality. You're doing the same basic thing across these different things, and aspects are used to capture that. With a single aspect in a single place, you can modularly characterize what has to be done in any state chart across the entire model. Get it to print out when it goes across the transition. That's one of the powers of aspects, and it allows us to do it in a very succinct way. We don't even see the code in those places it gets inserted. It can be inserted or turned off transparently to that area. We can specify where to put it in a crisp way in a single place. And Kurt's intuition is bang on, I think, that that in this case the occurrence of particles is a cross-cutting functionality here. In other words, systematically across this model, we see particles being used for stocks and flows. So the question is, could we try to do that through aspects?
Could each particle be taken, the details of each output from the particle be recorded by an aspect?
Right.
Used to start up a new particle based on
okay. So what I think would be very hard would be to have aspects somehow automatically automatically array these things, by particle. You'd have to do, I think, that arraying yourself. You'd have to go and sort of say, this is arrayed by particle, that's arrayed by particle. What aspects could be used to do is potentially to kind of put in place the mechanisms to process those particles. So like these mechanisms I showed you earlier, like receive empirical observation, process new output, update weights based on observation. You can potentially have aspect to do that. But as far as modifying the structure of the model, I don't think that would be too feasible, because you need to run the model forward simultaneously on thousands of particles, and you're not going to be able to tell Anylogic run once, run twice, run 3 times so easily, without doing a lot of work with snapshots, which would be pretty expensive.
Why couldn't you just, if you're going to, an agent base is more computationally intensive, so even if you could run 10,000 agent-based models at the same time, that's 10,000 times however many agents you have in each one. Right?
Indeed.
So that, regardless, you're not going to be able to make that computation friendly.
Except in a special language that's designed to be personal.
Okay.
Yeah. But not in Anylogic. It would be very expensive to do it in Anylogic. I do want to run hundreds of particles, maybe low thousands through the use of snapshots and so on, but it would be very expensive. Potentially you could run it once, take a snapshot,
But then I guess
go back
the
and run it
question
another
becomes, how much
time.
do you gain from, if the part of this is allowing you to have simple models, how much do you gain from having complicated models?
Well, the hope
If
would
you have a
be,
simple model that's being modified by
question.
data, so then what's the potential gain from it?
right. The hope would be that you could have a framework that would make it very easy to apply this technique. That, it would take minimal mechanism to put this into place. I mean, I think if we were to look at taking an existing simple model and in applying this to it, I think you could basically have most of that model up, in a day or so, or less. You could have the basic mechanisms in place, quite possibly in just a few hours. And that's pretty attractive, right? That model basically be able to be kept current with data in a couple hours time. To have it automatically, as it were, not quite recalibrate itself dynamically, but something close to that. Pretty attractive. That would be not disconnected. So these basic mechanisms are pretty simple conceptually, and they're pretty generalizable and standardized. You don't have to tailor this a lot. What does have to be tailored is the likelihood function. The likelihood function is quite specific. How likely it is you made the empirical observations given the underlying posited model state, the state of the system dynamics model. That's something which is tailored to your application context. The rest of it, receive empirical observation. If you process new empirical observation, update weights, normalize weights, initialize uniform weights, compute effective sample size, or resample indices. Those things are all boilerplate. Those things are all standardized stuff. It could just be reused. So I think the actual amount of work that's custom to your model is actually very small. Very small. So yeah, I would stand by probably a couple hours to get this going with a smaller model. With a bigger model that's subscripted by many other things, you would have to do a lot of looping over those other subscripts probably, because you need to. Is that true? I don't know that that's true. Depends if the likelihood function required it. In this case, you have to loop over the likelihood function. You need to apply the likelihood function for each particle, and the likelihood function for each particle, it might involve more than one subscript, etc. But not for particle. In any case, I don't know that even with multiple subscripts it would be that bad. It's pretty straightforward. So yeah, I think it would be that. So anyway, other questions? Questions?
So there's no other subscripts in this model, it's just the particles.
Just the particles in this one. But I was thinking, let's think this through. Suppose that let's suppose for sake of simplicity that this model were to be subscripted by H category, right? If this model were subscripted by H category, how would that change things? If we were subscripted by H category, the same basic mechanisms would apply. We'd receive an empirical observation. Processing it would require, as before, updating the weights. How would it involve updating the weights? Well, it would involve updating the weights in a pretty similar fashion to before. Namely, we'd have to go through, let's stop this, each particle, and then we would need to apply the likelihood function and multiply that pre-existing weight times that likelihood function. So we need to loop through the particles, and then we need to compute the likelihood function that asks what's the likelihood of seeing the empirical data in light of our posited model state, right? That's where the other subscripts would potentially come into play, in the sense that, okay, if you had a model with these age categories, maybe you'd have empirical data broken down by age category. Or maybe you wouldn't. Maybe you just have a total count, but you certainly need to work with an auxiliary variable in the system dynamics formulation in Anylogic, which is aggregated over age categories. That wouldn't be bad, dealing with a single number. If you had to deal with, for each age category of observations for each age category, well, you need to take that into account in your likelihood function. And I don't think that would be that hard to do. I mean, it's just, you probably loop over all the age categories in the likelihood function and multiply the probability, the likelihood of observing each one conditional, the reported incident count given the posited underlying incidence for age category I in both cases, and then over pi for all I, so multiplying for all I. I don't think that would be that bad. It would really come in the likelihood function, and then you update the weights and so on, I don't think that's bad at all. I mean, after all, there's only one weight per particle. It's not like your particle would have to be subscripted by age category. Particle would just be subscripted by the weight would only be subscripted by particle. And you'll notice, this is important. This weights thing, that's a big omission on my part. This weights thing here is, you'll notice that there's a weights, where is it? Where is weights? Okay, come on. It's system dynamics, weights. Where is weights? There it is. Boom. Here's weights. You notice that there's one weight per particle. So, in short, this update step that occurs, update weights based on observation, this is virtually unaffected by the presence of other subscripting, with the exception of the likelihood function. The likelihood function is where it's at. There is one other place I'll come to. So basically we have very boilerplate sort of code here. It's all, what has to be customized is whatever's in this function. We still have this function call, it would just compute a different thing based on the other subscripts. But one thing I haven't shown you is this other thing that actually updates the weights. So you'll notice when we resample and update weights and parameters, we do update particle values with resampled indices. That's this guy. Let's go take a look at him. Here we go. This also is model specific. So here, you notice what I have is I have for each value of the stock in the model, I actually have an array that knows, basically this array, these arrays remember the state associated with a given particle. And it's a kind of complex process, but basically I need to be able to assign what's in, say, particle 1 without destroying all memory of what was in particle 1. Because particle 1 might be, the future particle 1, the posterior particle 1 will have in general a different value than the prior particle 1. But that prior particle 1 might not go to the posterior particle 1. It might be duplicated in numbers 2 and 3. And so I have to kind of remember it. And so here we do this, and then here, we're having gathered all the data in temporary arrays, we don't have to now worry about overwriting that. Now we can update the state accordingly. So for a particle I, which is told to assume the value of a particle j, overwrite the states of I with the states of j. So if we're told particle 1 is overwritten by particle 2 state, we go through here and we update that. Now that we safely have squirreled away, we've remembered away the state of particle 1 elsewhere in these arrays. So in short, I set the value of susceptible, exposed, recovered, the value of C, etc. So these are all updated here. So this code would also need to be modified. So in short, for the modifications for the Krugerian, with a Krugerian question and with the issue of multiple of stocks that are subscripted by additional things, really it'll be this method and Cheryl, this method with the likelihood function, this guy here that we looked at earlier. So he's going to get a count. So this likelihood function would be different. Does that make sense? Yeah. Okay. Yes.
In this model, how do you define the system noise, the negative noise?
Okay, that's a great question. So there's no noise matrix like there is in the Kalman. So in the Kalman filter, as you know, we have a process model with assumed Gaussian white noise that's characterized by so these Gaussian perturbations that are governed by it's a Wiener process of a covariance matrix, right?
Yeah, I mean, it's kind of non-necessary to be the noise matrix. It's kind of being the description of how the noise distribution looks like.
Right, and the idea is that the model is fallible and it's described by a noise, its evolution is described by a noise matrix. So we believe the underlying process out there in the world is only imperfectly matched by the model, and specifically that it deviates from the model according to this Gaussian noise process, right? And so there's some sort of random walk away from the model, and we have a covariance matrix. What is it, Q or P?
Yeah, whatever it is. I mean, the notation isn't that.
Yeah, it's not that important, but it's there's a standard one, Q or P, that's used for it. And then there's in this case, there's no noise matrix imposed. And so it's not assuming any linear form, assuming a covariance between these different random variables associated with the model state. Instead, we can impose any sort of noise process we want. But let's be very clear. Suppose we were to not have any noise in the model at all. Suppose in this system dynamics model, we just had it ran in a totally deterministic way, right? We give it these parameter values, suppose the parameter values are fixed, and it produces an output accordingly. It'll be a fixed output, say, prior to the first observation, right? So the model here is, so here's the system dynamics model. We give it some initial state, suppose that's fixed, and it's outputting precise thing. Okay, now the first observation comes in at time t, right? First observation arrives at time t, suppose. So this observation has a certain empirical set of values, and we then go through. So what's going to happen, we're going to have this receive empirical observation. When that happens, we're going to process it, and the first thing we do is we're going to update the weight
based on the observation. Right now, all the particles have the same value, right? All particles have an identical value because they're all leading to this. And now, we're going to be adjusting here the weight. So here we have the infectious incidence for the period as the empirical data, and then we give it as our information this number completing the latent period, and here what we have is a situation where for all the particles this is going to be the same, this is going to be the same, and therefore all of them are going to have their weights updated in an identical fashion. And it's going to then, have still a situation where all their values are the same. Eventually it will resample them, but they're all the same value, so it doesn't matter. So in other words, in this sort of situation, when empirical data comes in, this model is going to continue with a fixed, it's going to be a deterministic model. Whatever it does, you're only going to have a single value. There's no dispersion going on, and there is no uncertainty that's been induced here at all. Why not? Well, each particle is showing a different possibility, but all the particles are initially the same, and never is that symmetry broken. They always stay the same. A new observation comes in, that updates their weights, but it doesn't introduce any new diversity in them. You see what I mean? And so it continues on in a deterministic way. Instead, within this model, what we have is we have a situation where we are imposing a random process associated with two things. Number one, we have this sort of Poisson arrivals going on here. So we have a force of infection, and we integrate this model. Instead of having a smooth number of people go down here, we treat it as Poisson distributed for any time step. So with this tiny delta t times force of infection times the number of susceptible. And second of all, we have evolution going on here in context per week, in the log context per week. So here we have evolution going on in the number of in the value posited for the C parameter, the contact parameter, contacts per unit time parameter. And those distributions, or the processes used to describe those, could be anything. In this case, I had normal perturbations to this parameter value. So that is quite similar, normal perturbation to a log of this parameter value, to a log of it. So in other words, it was geometrically being perturbed in a multiplicative way. And similarly, this was a noise process associated with number actually getting infected. So if the force of infection was very small, sometimes you might see 0, sometimes you might see 1 person within, getting infected. So in other words, we don't have to impose a matrix. We can just describe whatever type of stochastic process, and that stochastic process will now induce a spread of this trajectory that will then get corrected. It will induce a spread of the trajectory. So in short, we would want to introduce some sort of a process that spreads it. Now, one way to do that, again, is to introduce stochastics within the model. Another way to introduce it would be to associate each parameter value, or associate at least one parameter value, one initial value, with a distribution. And the issue there, though, is that if a given particle is reproduced, it will never change. It will never change from the other copies of itself. Within this current model, the particles are evolving. So if a given particle is reproduced, so 2 copies of itself, let's take on the board here, this particle here is copied 4 times. With the current model, that will yield to divergence of those 4 because there's this noise process that's kicking them around. Does that make sense?
Yeah, I think so. If I copy those particles, if everything are just identical without introducing the non-deterministic, that would be just sounds that in the model you have that like in the model we won't consider the system noise. So if consider the system noise, we actually using the stochastics of the particle evolves to actually representing the noise distribution that imposes on the deterministic way of how the model should evolve.
Okay, sorry, say that again. You lost me there for a second.
Okay. So in particle filtering.
Yes, in particle filtering.
From then for sure then in
Kalman filtering. Yeah.
Well, you're trying to express the noise of the system noise model.
That's right.
Instead of directly using a parametric distribution.
Correct. Yes.
Yeah. You're basically using a random process to representing what kind of the values are going.
Yes. You expressed it better than I did. Exactly. So in Kalman filtering, what we're imposing is the assumption of a parametric process. It's a parametric process in the form of a Gaussian white noise process with covariance matrix Q or whatever, and similarly in Kalman filtering, I might add, we're assuming a parametric measurement process with covariance matrix R, I think, if I'm not mistaken, if I remember the notation, and that's assumed to be Gaussian, a Gaussian process. That's assumed and that can be a real issue when you have small numbers, for example. For example, when you have small numbers of cases of TB in your population, assuming a Gaussian noise process can lead you to posit non-physical things like negative people with tuberculosis. And same thing with the measurement process. You're assuming that the noise is normally distributed. You're assuming that you can get negative reports of people. Whereas, and that's in Kalman filtering, it has those distributional assumptions, and that affords it great power in terms of some analytic results, which allows you to identify the MLE solution, right? You can do a very nice analysis based on Taylor expansion, etc. But in this case, with particle filtering, you're not imposing those distributional assumptions. Fundamentally, you're not imposing this parametric or straitjacket on it. And you can just describe any number of different processes which affect this, some of which might have Gaussian distribution, some of which might be Poisson distributed, some of which might have a binomial, or whatever you want. And you can impose that, and it's a noise process. Just be aware that absent of stochastics of this sort, you may get this creeping degeneracy. I thought it sounded good too. This creeping degeneracy, whereby the number of particles becomes, the state of the particles becomes impoverished, because more and more particles are reproduced in a hideous clone-like fashion. So they all have exactly the same values from then on. And you get this growing hegemony of just a few particles, which
which you generally don't want. And partly for that reason, it was honestly partly for that reason that I introduced this perturbation process on C here, that I knocked C around, boom, 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 boom. I was knocking C around, so you wouldn't get this creeping degeneracy and hideous hegemony.
That's also a useful way to actually implement.
Yeah.
For sure, this not only kind of take into consideration of the system noise, but also kind of solve it in a computational way to prevent those largely scale similarities of
That's right.
particles at the end.
That's exactly right. So we could run this were there only time on with no noise processes at all, and you would see the manifest results of those processes, and it'll be in the form of this degeneracy. Yeah. Okay. Now, I would love to do this, but my thought would be to use the balance of the time that affords us that we're afforded this afternoon to actually do a little bit of profiling. What do you think?
We have 20 minutes.
Who would prefer seeing creeping degeneracy and hideous hegemony? Okay, shall I do the profiling?
Sure, we only have 20 minutes though.
Yeah, exactly.
Sure.
Yeah, no. I think the profiling is compact enough.
That's 3 times longer than you had last time.
Okay, so let's